Okay, today we are going to work our way through section 7.2, which focuses on using the law of sines to solve oblique triangles. Now we've been focusing on right triangles, but not all triangles are right triangles. When we have right triangles, we have worked through our unit circle trig and our right triangle trig approaches to solving those right triangles. Unit circle trig, we have our angle set in standard position so that we create our right triangle based on that angle being in standard position. When we don't have our angle in standard position, where we can use x, y, and r as our values, if we just have a right triangle floating out here in space somewhere, then we identify what angle we're interested in, and we talk about the sides as being opposite, adjacent, and then of course the hypotenuse is opposite that right angle. But not all triangles are right triangles, so we need methods to deal with to solve oblique triangles. Now, an oblique triangle is just one that does not have a right angle. Oblique triangles can have all acute angles, or two acute angles and one obtuse angle. Remember that the sum of the angles in a triangle has to be 180 degrees. So where we had a right triangle, one of those angles was 90, and that meant the other two were complementary. Their sum had to be 90. We don't have that luxury of that starting place when we're solving an oblique triangle. We know that the sum of all three angles still does have to be 180 degrees though. There are 4 cases to solve these triangles, and the case is determined by which pieces of information we are presented with. So the first one is where we know one side and any two angles. Now, if I know 2 angles, I automatically can figure out that third by going back to the concept that the sum of the 3 angles is 180 degrees. Order doesn't matter here. And when I talk about order of the sides and angles of a triangle, we label our side by the name of the angle opposite. So angle A is opposite side A, angle B is opposite side B, angle C is opposite side C. My angles have capital letters, my sides have lowercase letters. If I know any 2 angles, and it doesn't matter, for example, if I knew A and B, it doesn't matter which of the other 3 sides I know. I have set up the proportionality of the triangle and the size of the triangle. The second case is side-side angle, where I know 2 sides and 1 non-included angle. That's my ambiguous case, and that's the one that gives us some fits. We're going to focus on it today. That's my ambiguous case. It's ambiguous because depending on the measurements, I might have no triangle, 1 triangle, or 2 different triangles defined by those 3 measures that I'm given. My third case is side angle side. Now notice I have the same basic 3 pieces of information, but this time that angle is included between the 2 sides that I know. For example, if I'm dealing with side angle side, if this is my angle, then that means I would know sides C and B. Side angle side. This angle is included between the 2 sides. And finally, my fourth case is when I know side, side, side. All 3 sides. 3 angles doesn't help me. For example, if I have a 60, 60, 60 triangle, all I know are that the 3 angles are all 60 degrees, that tells me nothing about the size of the triangle. So if I know 3 angles, I know whether or not the triangles are similar, but I don't know that they're congruent. Law of sines will help us solve these first 2 cases, where I know 2 angles and 1 side, or my ambiguous case. The theorem for law of sines says that I can depend on each of these ratios being equal to each other within a triangle, because the triangles are proportionate. So that the sine of A compared to the length of side A is equal to the ratio with B, and is also equal to the ratio of C. Now, the way I stack these, whether I put sine on top or the angle or the side measure on top, makes no difference. We're also going to remember that the sum of the angles in a triangle is 180 degrees. Okay, a quick proof of our law of sines. If we look at an oblique triangle, now this triangle is any triangle, but I have dropped an altitude and height down from the vertex perpendicular to the opposite side, which forms the base. Well, if I'm focusing on this entire triangle, but then I break it down, so I have two right triangles here, I know that the sine of side A is opposite over hypotenuse, so this would be h over c. And I know that the sine of angle C is going to be opposite over hypotenuse, which in this case is h over a. If I solve each of these equations in terms of h, so for this first one, I'm going to multiply c over so that I have h equals c times sine of a. And for the second equation, I multiply a over so that I have h equals a times sine of c. Now, because both of these are equal to the same value, they're both equal to h, and I know that h is equal to itself because I've used that same measurement for both of those triangles, then I can set these two things equal to each other so that I have c times the sine of a is equal to a times the sine of c. Now, I can rearrange terms so that I end up with this proportion. Now, the way I'm going to rearrange terms, and we can start wherever we want to start. If I divide both sides by c, that cancels over here. And then if I divide both sides by a, that cancels over here. And I'm left with this proportion. And that proportion is also going to be true if I move where my altitude went and I work in that other side an angle. Okay. Excuse me, pages don't want to turn. All right, law of sines in a triangle with an obtuse angle works basically the same way. The difference identity, we're going to call it a difference identity instead of a difference formula for the sine function. It can be shown that the sine of an angle supplement, so 180 minus a, if this is angle A, then this value of this angle is its supplement, 180 minus A, because together they form a straight angle. Difference identity tells me sine of 180 degrees, cosine A, cosine of 180, sine of A. Well, sine of 180, think about your unit circle, 180 is over here at pi. Sine over here is 0. Cosine over here is -1. Anything times 0 is 0, minus a negative sine A gives me sine A. Like expression 1, therefore we would use SOHCAHTOA, our right triangle trig rules for opposite, adjacent, and hypotenuse, to complete the ratio so that sine A equals this height over that's going to be opposite over hypotenuse. And that shows me the same type of proof, but this time with an obtuse angle, obtuse triangle instead of the acute triangle we started with. Now, you're not going to be asked in this class to formulate the proof. We're just showing you why those proportions are always true. Now, if I'm solving for a side angle or angle side angle, the order in this case does not matter. The important part is I know two angles and one side. Always, 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 for all of these triangles, do your sketch first and make sure that you label carefully. Making sure things are correctly labeled is key to solving these triangles. So we're solving that angle side triangle. And we're starting with 3 pieces of information, and we have to solve by finding the other 3. Whenever we're given a choice, use given values, not found values, because if you make a mistake when you're finding something, then you're just going to compound that error. If you're using your givens, you know you're starting with correct values. So found values could be wrong. And usually those found values are approximations. We've already rounded them off. So if possible, we want to always use our givens as we're solving a triangle. Okay, sketch and label your triangle ABC. We don't have a right angle, so it doesn't matter. Really, if our sketch is proportionate, we're just going to sketch so that we can label correctly. Angle A is 20 degrees, angle B is 80 degrees, and side A is 4. Side A has to be opposite angle A. So the pieces of information I need angle C, I need side C, and I need side B. Well, right off the bat, angle C is where I'm going to start. Because I know that the sum of the angles in a triangle are always 180 degrees, if I have 100 degrees already used up, that means this remaining angle has to be 80 degrees. So I've already done the 1/3 of my solution. Next, I need to solve for these remaining two sides. I'm going to use the law of sines. I'm going to start with the pair I know. Well, the pair I know is A. And I can stack it whichever way I want. I'm going to choose to put the side length on top. And I know that this ratio is going to be equal to both of my other ratios involving B and C. So I can say that side B is over sine of 80 degrees. And then once I'm ready, I can talk about the fact that side C is going to be in a ratio with the sine of, and then this one is also 80 degrees. Because these two angles are the same and our triangles are proportionate, we know that these two sides are going to have the same measure. Because triangles are proportionate, the longest side is opposite the largest angle, shortest side is opposite the smallest angle. If these angles have the same value, then the sides opposite them must be the same. So really, this is the only thing I have left to solve, because once I know the length of B, it's going to be the same for the length of C. When I solve proportions, I use cross products. So I find my cross products, 4 times sine of 80 degrees. That's going to be equal to B times the sine of 20 degrees. I'm solving for B, so I'm going to divide both sides by the sine of 20 degrees. And B is equal to, and this is just what I plug into my calculator. So make sure that I am in degree mode, and I'm not. In degree mode now, I'm going to do 4 times the sine of 80 degrees. And I'm going to divide that by the sine of 20 degrees. And that leaves me with a side length. Now I'm going to have to round this off. We're going to go ahead and just round to 1 decimal place here. Make sure you pay attention on my math lab and on the written homework what it tells you. We're going to round this off to 11.5 units. And we know because this is an isosceles triangle, we have two angles that are the same. Both of those side measures are also going to be the same. So we already know side C. Okay, let's look at the next example. Now, this says example 2. It doesn't give us what type of triangle we're solving. Let's do our sketch. ABC. Remember, it doesn't matter if it's proportionate. When we do our sketch, we're making sure we label things correctly. B is 25 degrees, C is 85 degrees, and we know side A is 6. Those are the 3 pieces of information we know. So I'm solving for angle A, I'm solving for side B and side C. Well, we know angle, side, angle. So that is the case that I'm solving. That's just like the case I just had. Even though our givens were in a different order, our givens were side, side, angle, or excuse me, angle, angle, side here. Here it's in the order angle, side, angle. I still have the same basic 3 pieces of information where I can start by figuring out angle A. Well, because my sum is 180, I already have 110. Angle A has to be 70 degrees. So this triangle is not isosceles, it's scalene. All 3 sides are going to be different measures. Because triangles are proportionate, I know that side C is going to be longest. It's going to be longer than 6. And I know that side B is going to be the shortest. It's going to be shorter than 6. So I can kind of keep those things in mind as I solve to make sure that my answers make sense. Okay, the pair I know A. So I know that sine of A over 6 is going to be equal to the ratios. Sine, oh, you know what? We know A. Let me fill in for A. I get to talking and writing and I don't always get everything where I need it to go. We know that A is 70 degrees. We know that 25 degrees is opposite side B. And we know that the sine of 85 degrees is going to be opposite side C. So these are the two things I need to solve for. Side B, side C. And my B's look like 6s. I'm sorry about that. All right, let's do, it doesn't matter, let's do this one first. So 6 times sine of 25 degrees is equal to B times the sine of 70 degrees. So when I plug this into my calculator, 6 times the sine of 25 degrees divided by the sine of 70 degrees, I get 2.7. We're going to round that to 2.7 for side B. Well, that makes sense. B is my smallest angle. That should be my shortest side. And then I'm going to jump over here and I'm going to say, okay, this is the pair I know and the ratio that I need to solve for C. So C times the sine of 70 degrees is 6 times the sine of 85 degrees. And I divide by sine of 70. So C is going to be equal to this value plugged into my calculator. 6 times the sine of 85 divided by the sine of 70. And I'm going to round that to 6.4. Largest angle is angle C, opposite the longest side. Smallest angle, angle B, is opposite the shortest side. All right, so we have solved this triangle, completely solved the triangle. Let's move on to our ambiguous case. Now, this is the ambiguous case because based on the information that we're given, there are 3 possible ways it could fall out. One scenario is that there are 0 triangles. It doesn't work. Or there could be 1 possible triangle, or there could be 2 unique triangles that are defined by the given measurements. It writes at SSA, if you think about it going the other direction, it is definitely a pain. So we want to figure out if it works for 1 triangle, we have to check for a second. If it doesn't work for the first, it just doesn't work. All right, let's start with our sketch. Always start with a well-labeled sketch, ABC. Angle B is 35 degrees, side B is 5, and side A is 3. So you can see we've got angle, side, side. That's my ambiguous case. Angle, side, side, and we're going to figure out how many solutions we have here, but we know it's ambiguous. So we have 2 angles we need to solve for, angle A and angle C, and we need to solve for side C. I have a pair. I have that B, have all the information I need about B. So we're going to start there. For our first triangle, we're going to say, okay, we've got sine of 35 degrees over 5. And then I have to solve for A first because I don't know anything about C. A is the thing that I know something else about. So we're going to solve for angle A. It's a proportion, so I solve using cross products. So I have 3 sine of 35 degrees equals 5 sine A. Divide both sides by 5. Now when I plug this into the calculator, it gives me the sine function value of angle A. So angle A is going to be equal to the sine inverse of whatever that comes out to be. And don't round until you're done. I usually will start here. I'll do 3 times the sine of 35 and then divide that by my 5. That's my sine function value. Don't round that off. Use sine inverse, so do second sine, and then bring that back up using your calculator. So second answer is going to bring up that sine function value, and it tells me that angle A has a value of 20.1 degrees. So A is approximately 20.1 degrees, and we've solved for A. Now I'm going to make this A sub 1 just in case we have a second triangle. We've got to stop and remember to check to see if we have a second triangle. Well, if angle A is 20.1 degrees, and I know that B was 35 degrees, that's 55.1 degrees. That means that angle C has to be 124.9 degrees because the sum of those three angles adds up to 180. All right, so this is my first triangle. There may be a second, but we've got to finish solving. We've got to finish by solving for side C. Well, to finish, so that's the first step, that's the second step. Third step here is to solve for side C. I start with my known pair, sine of 35 degrees over 5, and then I have a value for angle C. So sine of 124.9 divided by side C. I solve for C. Dividing both sides by the sine of 35 degrees. And I get 5 times the sine of 124.9 divided by sine of 35. I get a length of 7.1 for length of side C for this first triangle. Well, does that make sense? Angle A is my smallest angle, 3 is the shortest side, angle C is the largest angle, and 7.1 is my longest side. So yep, we're in good shape. Okay, so that's my first triangle, but is there a second triangle? With the ambiguous case, if you have a first triangle, you have to check for a second. All right, so what do I check? Well, I go back to that angle that I found. My first found angle was A. That was the one I had some information about, so that's what I found first. So I go back to that A sub 1. Now, remember on the unit circle, when you are reflective properties of the unit circle, if I have an angle in quadrant 1 that has a specific sine function value, sine is positive in quadrant 1, sine is also positive in quadrant 2. So I'm going to have another angle in quadrant 2 that has the same sine function value. If this were a 30-degree angle in quadrant 1, quadrant 2, the angle in quadrant 2 that has the same sine function value is 150. You can check that on your unit circle if you want. They both are the same distance from the x-axis. So these two angles that have the same sine function value are going to be supplementary. They're always going to add to 180. So for this particular case, my angle A that I found was 20.1 degrees. It's going to be right here, right? 20.1 degrees. There's another angle in quadrant 2 that has the same sine function value. It is going to be 20.1 degrees away from the x-axis, away from pi. So to figure out the value of that proposed second triangle, angle A, I'm going to do 180 minus 20.1 degrees because that tells me what that angle would be that has the same sine function value as this one. And in this case, I get 159.9 degrees. So that, if I have a second triangle, that's the value for my angle A. Now, I have to add to that the given angle. And my given angle for this triangle was B. B is 35 degrees. It just is. If I add these two together, I get 194.9 degrees. And that is too much to form a triangle. That's more than the sum of the three angles in a triangle. So there is no second triangle. That sum of these two angles alone is more than 180. If it had been less than 180, then my second triangle would have worked. Okay. Move on to our next example. I'm trying to skip a page. There we go. So if I'm using law of sines to solve side-side angle, again, this is ambiguous. That triangle that we just worked only had one solution. There was only one triangle formed by that set of information. This one, we got to see how many triangles will be formed here. Always start with your sketch. We expect our ambiguous case. We need to make sure that we are labeling things in the appropriate order. I see I'm missing angle B, angle A, and side B. I have to start with what I'm given. So I'm given my pair that I know is about C. So I have sine 15 degrees over 6. And then I have to go back to angle A because I know the side A. So sine of A over 10. Now I know that angle A has to be larger than 15 degrees because side A is longer than 6. So when I solve using cross products, I get that 6 sine A is equal to 10 sine 15 degrees divided by 6. So angle A is going to have a sine function value of 10 times the sine of 15 degrees divided by 6. So I plug that into my calculator, 10 sine 15 degrees divided by 6. And then I need to figure out what that angle would be. So I take the sine of it, sine inverse of that, and I get an angle at 25.6 degrees. So A, my first proposed value for A is 25.6 degrees for that first triangle. If C is 15 and A is 25.6, that gets me to 40.6. I subtract that out of 180 and I would have 139.4 for angle C. So angle A is approximately, because I rounded, angle C would be approximately 139.4. Now I need to do, angle B. Good grief. Guys, I apologize. This is B because that's the one I didn't know. I already knew C. I found A. That means this one B. So now I need to do side B. That's my second step. Third step, I go back to my givens. Sine of 15 degrees over 6 equal to sine of, and we have to use that value for angle B to solve for side B. When you plug this into your calculator, you should end up with this side B being about 15.1 units, which makes sense, largest angle, longest side. Okay, we had one triangle that works. We have to check, because it's the ambiguous case, we have to check to see if there is a second triangle. If there is a second triangle, the angle that we found first, A, will have a supplement that is the angle A for the second triangle. So I take what I found and I subtract it out from 180. And I get to 154.4 degrees. And then I need to add my given angle. My given angle was C. So this would be A in the second triangle. Angle C was given as 15 degrees. And when I add those two together, I just have used up 0.4 degrees. So there's still room for a third angle. We do have a second triangle, because this has not made it all the way to 180 yet. In my second triangle, the angle A is 154.4, angle C was my given at 15, angle B for my second triangle is going to be whatever is left out of 180 here. So in this case, I've got 10.6 degrees for angle B. Now we need to find side B. So we go back to our given pair. And our new value for angle B, this time angle B is the smallest angle, so it's going to need to be opposite the shortest side. You should come out with a value of about 4.3 for the length of side B, where angle B is 10.6. So this particular ambiguous case triangle had 2 solutions. All right, example 5. Ambiguous case again, we got to figure out if we have 0, 1, or 2 solutions. Start with your well-labeled sketch. ABC, angle A is 50 degrees, side B is 8, and side A is 5. So angle, side, side. We're looking for angle B, angle C, and side C. So we start with the information that we know both pieces of when we know about A. So sine of 50 degrees is compared to a side length of 5. And then we can't do anything about C yet because we don't know anything, so we're going to go to B. Sine of B is over 8. Find my cross products. So 5 times the sine of B is equal to 8 times the sine of 50 degrees. Divide out by 5. So angle B is going to have a sine function value of 8 sine 50 degrees divided by 5. I come over to my calculator and I say, okay, 8 sine of 50 degrees. I divide that by 5 and I get a red flag. Remember our limits for sine and cosine? Sine and cosine are x or y compared to r. They're always going to fall between that middle section from -1 to 1. This is bigger than 1. So if this is my sine function value, let's see what happens. When I do sine inverse of that value, it gives me a domain error. Because that 1.23, this comes out to be about 1.23, that is outside the domain of sine, which is the range of sine inverse. Excuse me, the domain of sine inverse. Sorry, I said that backwards, which is the range of my sine function. And when that happens, this triangle does not exist. D and E does not exist. There is no solution. There are 0 solutions. With that information, there's not a triangle that's made. Okay, so that's some practice applying our law of sines. Let's do a couple of problems that are application problems that actually put our law of sines and our idea of solving these oblique triangles to work. So John needs to determine the height of a tree before cutting it down. He wants to be sure that it's not going to hit the fence. When the tree falls, it needs to fall without hitting anything, right? The angle of elevation of a tree from one position on a flat path from the tree is 40 degrees. The angle of elevation, so path looking up to the top of the tree is 40 degrees. From a second position further along, it's just 30 degrees because when I scooch out, that angle gets smaller. What's the height of the tree? All right, so we've got the path. We've got our tree here. There's our tree. The top of the tree is up here. We need to know where that top is going to fall. We don't know how high the tree is. We're solving for the height of the tree. If I stand over here on the path, my angle of elevation is 40 degrees. And then if I move back 20 feet, I need a straight edge for these, don't I? My angle of elevation is now 30 degrees. So basically, I've created a right triangle that I could work with, but I also have this this oblique triangle here. So I've got this oblique triangle that I can work on based on the information I'm given. Well, if this is 40 degrees, this angle is 140 because they are supplementary. They form a straight angle. If this is 140 and that's 30, that makes this angle 10 degrees. And I know that this distance between my two spots A and B is 20 feet. So, you know what? I stated that wrong. The height of the tree isn't as well. It is important because when it falls, we want to make sure, we want to know how far it's gonna go down. If we get this, we're gonna be able to solve for the height. That's what I'm after. Ultimately, I've got sine of 40 degrees is opposite over hypotenuse. Sine of 40 degrees is opposite over hypotenuse. The height of the tree, h, over this hypotenuse. So I need to know what this hypotenuse is. Sorry, I jumped right in and didn't evaluate what I was solving for. I'm going to get this value so that it's the hypotenuse for this right triangle. There we go. All right, so back to my oblique triangle, 30, 140, 10. I know this pair, so I can use sine of 10 degrees opposite 20 feet. And I'm going to solve for this side, so I'm going to use angle B because it's opposite this side. So sine of 30 degrees over whatever this side length is here, B. That's what we're going to solve for. So B sine of 10 degrees is 20 sine of 30 degrees. So when I divide both sides by that sine of 10 degrees, I've solved for the length of this side B. Oops, domain error. 20 sine of 30 degrees divided by the sine of 10. And I get, let's keep it a little bit more exact right now. So let's do 57.59. It's about 57.59. So if this is 57.59 feet, then to solve for the actual height of the tree here, I'm going to do this hypotenuse, 57.59 times the sine of that 40-degree angle, and that's going to give me the height of my tree. Now I've still got this right here, so I'm just going to multiply this times the sine of 40 degrees. And I figure out that my tree is just a little bit over 37 feet tall. Make sure that when you're doing application problems, you put units in with your answer. All right, so last applied problem. Then we're going to be done for this section. Two fire stations are located a half mile apart at points A and B. There's a forest fire at point C where the measure of angle B is 41 degrees and the measure of angle A is 47 degrees. Draw a sketch. So A and B are a half mile apart. And there's a fire up here at C. It's going to be maybe a little bit closer here. That's going to be 47 degrees. And that one's going to be 41 degrees. Notice that when I label angles with three letters, it's the one in the center that is the vertex of the angle. So what do I know? I know that I've got side B over here, side A over here. That's my sketch. That's what I know. Justify how you know without any computation that fire station A is closer to the fire than fire station B. Well, remember I mentioned about up here when I move further away, that stretches that angle out and the angle gets smaller. So when the angle is smaller, this side is shorter. Angle gets larger, this side is longer, which means the fire is closer to station A because side B is shorter than side A. It is opposite the smaller angle. Use law of sines to calculate to the nearest tenth how much closer station A is to the fire than station B. Now notice how much closer. So I need to know the lengths of both of these sides. And then I need to compare them. Well, to figure this out, I need to know angle C. So 47 plus 41 out of 180, not minus 180. 180 minus that sum gives me a 92 degree angle here for angle C. So we're going to do sine of 92 degrees over, and I can leave this as half a mile because we're interested in an answer to the nearest tenth of a mile. We're not needing to switch to feet. So I'm going to do sine, let's just do sine of 47 degrees over A first, and then we're going to come back over here and do sine of 41 degrees over B. So we'll find A and then we'll find B, and then we got to compare them. When you plug this into the calculator, I'm going to keep more decimal places now so that I can round it better when I get to my answer. That's about 0.366 miles. So that's about 0.366, not 3.6. 0.366 miles. Over here, when I plug B, when I solve for B, plug it into the calculator, I get 0.263. So side B is about 0.263. When I compare those, when I subtract, I figure out that station A is about 1/10 of a mile closer to the fire. Because that distance is just 1/10 of a mile shorter than the other. All right, that is all for 7-2.